Alright, so this is an interesting area, looking at rates of reaction that are chemical kinetics. And I mean, look, it's as simple as, a chemical reaction in which you've got an explosion means that a chemical reaction takes place very quickly, and an extremely loud bang is heard. I mean, that's straightforward. On the other hand, chemical reactions like rusting or food ripening take place over several months. So it's just really important to know what sort of rates we're talking about then with chemical reactions. And when you consider then if it's an industrial production, chemical production, you're going to want to know then how much reactant is consumed or how much product is produced in a given time, because these kind of constraints are important then in production of chemicals. And then what are the elements that can speed up or slow down a chemical reaction, like for instance catalysts, temperature, pressure, that kind of interesting stuff, and even the nature of the actual reactants. Okay, so here's our list then: factors that affect rates of reactions: concentration of reactants, temperature, surface area. So the more substances are broken down to increase their surface area, the better the reaction. And the use of catalysts then, as well as this list, you've also got the nature of reactants, meaning that if you've got substances that are ionic reacting, you're going to have a quick reaction in that case. Whereas if you have an ionic substance and a covalent substance, bonds are going to have to be broken in the covalent molecule, and so that is going to slow down the rate of reaction in that case. Okay, for concentration, then look at if you've got lots of humidity in water, for instance, then rusting is going to happen a lot quicker, as opposed to in a less humid environment. You've got less water in the reactants side of things, so the rate of reaction slows. Cooking an egg is a chemical reaction. It can't be reversed. It's not a physical reaction. So what that means then is the egg will cook quicker then if the temperature is increased. So that means that the rate of the reaction increases if you increase temperature. Great example of surface area. Chewing food breaks down the food. It initially has a given surface area, but when you break it down, you expose the inner parts of the substance, the food that you had, and so therefore you increase the surface area. Okay, and this increases the breakdown of the food then, and the reaction involved in that. In a mill, you've got a buildup of charge with the grain. When it's ground down, it becomes very small dust particles, and so therefore you've got a greater surface area, and in this case, if the charge isn't controlled, you can end up with an explosive mill fire. Catalysts then increase the rate of reactions. So for instance, if you've got poisonous carbon monoxide or nitrogen oxide and nitrous oxide, and you want to ensure that they're catalyzed when they go through the catalytic converter, you have the presence of a catalyst then to ensure that this reaction is speeded up so that you get safe carbon dioxide and nitrogen gas released from the exhaust. Okay, so our reaction rate then, very importantly, in a chemical reaction, the changes in the concentration of reactant or product. Okay, so when a reaction takes place, you initially have a concentration of the reactants, but as the reaction proceeds, you then have an increase in the concentration of the product. So the reactant concentration decreases and the product concentration increases. And this is the rate of reaction then. Molarity is the unit then that we use for concentration. So it's the change in molarity then that we use to compare and contrast reaction rates. Rate always involves time, and the reaction rate does certainly involve time, and it's defined as moles per liter, L to the minus 1, per second, okay, or as moles per second. Okay, a reaction rate with a typical example of a reaction then. So we've got our reactants on the left, we've got our products on the right, and quite simply you can see that in the presence of water and your hydrogen ions, you end up with glucose on the right hand side. You use these square brackets to represent concentration. So for instance, you put a square bracket around sucrose to represent the concentration of sucrose. And the delta sucrose, or the change in concentration, is the concentration, the second concentration minus the first concentration. So the first would have been the initial starting concentration, and the second concentration would be after some reaction time. And the change in time that we're talking about then is time 2 is after time has elapsed, and time 1 is at the start point, and that's our delta T, or change in time. Reaction rate then really simply is just time it takes, the time that's elapsed, and the difference between the beginning concentration and the final concentration, or delta sucrose over delta T. And it's as simple as that. That's our reaction rate. Okay, so when we calculate our rate of reaction then, this value is going to turn out negative, to be quite honest. Since concentration of sucrose at time 2 is going to be less than the concentration at time 1, and we're taking the concentration at 1 away from 2, so we're going to get a negative value for our rate of reaction. But by convention, rates of reactions are positive, so therefore we put a negative in front of it, and a double negative makes it positive then, to agree with our convention. Since this is all part of one system, and the rate at which the reactants are proceeding is the same as the rate at which the products are being created. So therefore, to measure reaction rate, we can also analyze the rate of concentration change for the products. And in this case, we're looking at for glucose, and the delta glucose concentration over delta time is the rate of reaction. And note that the product has no negative sign because this value is positive, and by convention we're to have a positive value. Okay, then of interest, if we're looking at the general reaction rate, then if we compare the number of molecules in reactants and products, if we compare the rate of disappearance of hydrogen peroxide, for instance, based on the formation of oxygen, then we're asking ourselves the question, can the rate be based on the disappearance of H2O2 or the formation of O2? So at some arbitrary time, if we compare the concentrations of these two, the reactant and the product, okay, are these rates the same then, is what we're asking. Well, by comparing molarities, we can see from the balanced equation that 2 moles of H2O2 are consumed to produce 1 mole of O2. So the answer is no to that. The reaction rate based on the disappearance of H2O2 is actually twice the rate of the formation of O2. Basically, to get these two equal to one another, then you've got to have the rate of the H2O2 disappearance to make it equal to the production or the formation of the O2. Okay, so in general what you do then is you take what's called the stoichiometric coefficient, this A here, the blue A and the blue B, etc. And basically what you do is you divide, okay, so it's 1 over A in this case. Now it was 2 if you remember H2O2, so that became minus 1 over 2. But in general, depending on the coefficient, whether it be 2, 3, 4 or whatever, it's going to be 1 over that value, will be equal then to 1 over reactant B, whatever coefficient that happens to be. And basically in that way then you can equate these rates to one another then. Experimentally then, a reaction rate is measured by actually monitoring concentrations over time and doing a plot. And then by analysing the graphs, you're in a position to measure reaction rate by working with the slopes, etc. As has been said, for the reactant, its concentration decreases with time, and on the other hand, you've got that the product concentration increases with time. Okay, so here we've tabulated the decomposition of H2O2, and you've got your time in the left column and you've got your concentration in the right column, and then following that you've got your graphical representation right here, the black line, and then you've got various slopes or rates. The initial rate of decomposition, this red would be the average at the midpoint of the decomposition, etc. Okay, so for instance then, to get the average rate of decomposition. Okay, so for our average rate of decomposition then, we're looking at the two endpoints of our graph, and you can see that on the right we've got our concentrations, the final concentration being read from right there. You see the value coming from over here. The initial concentration 0.882 coming from the very top of the graph here, and the time factors involved 600 at the very end of this reaction for decomposition, 600 seconds, and 0 for the start time, and then from that you get your average rate. For an instantaneous rate of decomposition then, we're looking at the red line right here. We've picked a center point on our graph at the 300-second time interval, and basically drawn a tangent to the curve at that point, and basically just get the slope of that red line then, and that will give you the instantaneous. So I mean, pick two peripheral points on the red line, like there and let's say there, two good points, and from that then you can calculate using your y2 minus y1 over x2 minus x1 and calculate your instantaneous slope. And for the initial rate of the reaction then, which would be the steepest part of the graph, the rate would be the highest at the beginning, the rate of decomposition. So what you're seeing there is this tangent that is the blue line, and again what you want to do is you want to get the slope of the blue line, the tangent, and that will give you the instantaneous initial rate of decomposition or